Now that we know the right way to traverse a single array when we're traversing it a single time, let's consider a more complicated case where we have multiple arrays and where we need to walk over it multiple times and in different ways. Matrix multiplication. So this is just standard matrix multiplication where A cross B produces a matrix C, and that's done by, for this particular element, at row I, column J. In C, we get the answer by walking over the ith row of A and the jth column of B. We multiply this number times this one and add it to the second number times the second number and add it to the third number times the third number, and so on. So you can see right away that we have a more complicated problem where we know that it's better to walk across an array from left to right instead of top to bottom, but it seems that matrix multiplication is making us walk over across at least one of them in the wrong way. So let's look at all our options here. We're going to look at the different ways that we can form these loops and see if there's any difference in the performance. In all variants, we're going to have to process n-cubed operations. That's because we're assuming an n by n matrix, and we have these three layers of loops, each iterating over n. So in terms of absolute time, then we don't really have any choices. What we might have some choice on, might have some control over, is the number of cache misses for those order n-cubed operations. Right? We also don't have any choice on the space. We're dealing with n-squared operation. Each of the matrices is n by n. As we look at this, we're going to make some assumptions about the cache that are common sorts of assumptions for when the issues that we're talking about matter. And that is when the matrices don't fit in the cache at all. When each matrix by its size, n squared, is much bigger than the cache size. For the purpose of making concrete calculations, we're going to assume 4 elements per cache block. So maybe we're looking at doubles and we have a 32-byte cache block or something like that. So in order to consider whether we have cache misses, the most relevant thing is going to be this inner loop. Right? If we can get a cache miss rate on the inner loop, then it will pretty much follow for the slower traversals of the outer loops. In this case, since we have k on the inside, that's how we got this horizontal line for A and vertical line for B and a single point for C. Right? So as C iterates over k, it's just accumulating into this one spot, but as we iterate over k for B, then we're going down a column. Right? And I've written this a second way just to remind you that I is staying fixed for that inner loop. This inner loop, k, is the only thing that's varying. So it's the second position that's varying for A, the first position for B, no positions for C. So in this case, mostly you can just look at the picture. As we computed in the simple single array case, if we walk across a row with 4 elements per block, then we know our miss rate is going to be optimal at 25%. And we know that if things don't fit in the cache and we walk down a column, then that's going to be pessimal, and so we're going to miss every time. That's a 100% or 1.0 miss rate. Meanwhile, C is staying put, so it's just going to be in the cache, so we don't expect any misses there. So the overall miss rate is going to be, the rate at which something fails is going to be 1.25. In this implementation of the loop, we are accumulating into Cij, so we're writing to memory every time in that inner loop. And we've talked about the fact that that could be bad for performance. Unless the compiler knows that C and A and B are all in different places, then it's forced to actually perform that update. So it'll be faster in practice to accumulate into a local variable sum and then write it in. But that doesn't actually have any effect on the cache miss rate as we're looking at. Whatever kinds of effect it would have, it would be in the noise compared to the effects we're looking at on A and B. So we're going to call this initial loop that we tried ijk nested that way. That's the ijk variant. And if we have 3 variables, and we can put them in any order for these loops, since we are just assuming that times and plus are associative enough and commutative enough for this particular problem. So if we can order ijk in any way, then we have 6 possibilities to consider. So that was our first one. ijk gives us a 1.25 rate. When we have jik, that is when we swap the outer 2 for loops, it turns out that doesn't do anything because we're just looking at the inner loop. And from the perspective of the inner loop, j and I are still constant, so we still get the same result. So let's do something besides swapping I and j. Let's move k around. If we put k at the beginning, and then instead of looking up a every time in the inner loop, since a depends only on I and k and I are the outer loops, we will just look that up once. So again, in the picture, we're just getting one element, and we have no cache misses in that inner loop. Meanwhile, since j is varying, that means we're walking across horizontally in B, and it also means we're walking across horizontally in C. And this is good news. This is actually an improvement compared to our previous strategy. We now have 0 misses for A, a 25% miss rate for B, and a 25% miss rate for C, which is a miss rate of just 50% compared to 1.25 misses per iteration before. So we found something that's better. Just remember the j at the end. That's what caused us to go horizontally across B and horizontally across C. That was good news. As before, it doesn't matter if we swap k and I. That has no effect because it's the inner loop is just varying j. So it's the j at the end that's important. We have two more to try. We have jki. So putting I in the middle. We tried j in the middle and k in the middle, so I is what's left. In that case, we're walking down a column of A, we're walking down a column of C, and of course that's the worst possible thing. We're going to have 2 misses per time in the inner loop, and that's no good. So if we try swapping the outside, kji, that's not going to do anything either. Forgot to update the title there, but kji is the same. The ones that end in I are the worst. The ones that end in j were the best. The ones that were end in k were kind of middle of the road. And the authors of the book have actually tried this experiment. They tried jki, kji variants, that is the ones ending in I, which are bad, the ones ending in k, which were medium, and the ones ending in j that were good. And this is a logarithmic scale. Lower is better because it cycles per time spent in the inner loop. And they varied the array size just to see how the improvements vary over the size. So we should expect, since as we move to a larger amounts of memory by increasing n, that we get out of different cache sizes, and we should see the jumps like we do in I and k. It turns out that the j line is flat here just because not only is walking through memory sequentially good for caches due to blocking, but the Haswell architecture includes some extra streaming that detects the case when you're walking through memory and makes it work even better. And so even without that, the one ending in j would be the best option, but we can see in practice it's way better.